All right, so up to this point, we've talked about table 3.4 in your textbook, which kind of gives you different silicate structures. And I've kind of been hinting at this predicting capability. So let's do an example of that. So here's our example that we're going to do. So you have the table, you either have it here on the slide or you can look it up in your book. But let's say I have a compound, and this one is lizardite. So lizardite is kind of named because it has an appearance of, kind of lizard scales and stuff. So it's kind of green and so forth. But it's a silicate, and its formula can be found here. So let's say you have, this is just an example, right? You have any silicate structure, the formula. So here I'm writing it for you. And basically, let's use the table to see if we can figure out what type of silicate it is. So go ahead and do that. So pause the video and then see if you can come up, based on this table and the formula, what type of silicate it is. And then come back and I'm going to go over this example with you so you can hopefully get the same answer together. All right, I want to make one quick note before we solve this problem. The video I used for solving this problem was for MSE 201. And so you'll notice that when I solve the problem, it doesn't have this nickel. It just has Mg3. It's the same thing. What this is saying is that in actuality, lizardite can either have magnesium or nickel, but there's whatever they are, there's 3 of them. So keep that in mind when you watch the next part of the video, but it doesn't change anything, just that you're going to see that it just says magnesium. So, all right, go ahead. All right, so to be able to predict the structure of lizardite, which I've rewritten here, again, we need to know the oxygen to silicon ratio. So let's go ahead and calculate that. All right, so if I count up all the oxygens, they're OH4, so that means I have 4 oxygen here, 9 here, so 9, and then I have silicon 2. Well, if I do this, I just show that I got 4.5, right? So when talking about the SiO4 tetrahedron, I told you that the oxygen to silicon ratio of 4 was the absolute highest we can have, right? So what's the deal here? So it turns out that we can have, in the overall compound, right, we could actually have more oxygen than what we see in this, but the oxygen is not part of this tetrahedron, right? And as it turns out, they've actually already drawn it or organized it for us in such a way to show that these OH groups are not part of this SiO4 network. So the OH groups are separate, right? That's a chemical group, hydroxyl group, that's kind of separate. And so they've already actually done that. And so we know that these don't count. It produces too high of a number. And so really all we're concerned about is the SiO here. And so that's where these are the ones that are networked together as part of this tetrahedron. And so instead, so this is not correct. So instead, we should only count these. And so our O to silicon ratio is 5/2. That gives us 2.5, right? And so if we go to our table there, we see that according to our table, going back, that gave us the infinite sheets, or you might call it the planar structure. So that's the kind of structure you would expect with a number of 2.5 relating back to, that's from table 3.4. So again, this was an example I wanted to show you where they've actually organized it for us such that this part, those oxygens don't contribute. When we talk about the oxygen to silicon ratio, we're just talking about this form. So most of the ways that you're going to see these compounds written, they've actually separated it out for you to make it more convenient to do that. So that's how we can predict silicate structures.